In the grand cosmic theatre, there are forces so fundamentally opposed they seem destined for a confrontation. One is a behemoth of incandescent fury, a star that forges reality itself in a cauldron of thermonuclear violence. It is the heart of our world, the anchor of our existence, and yet it is a monster of unimaginable power. The other is a whisper from the void. A fragile traveller born in the deep cold silence where sunlight is but a distant memory, a ghost composed of ice and dust remnants from the dawn of creation. One represents the unrelenting explosive present, the other the serene frozen past. For aeons they have occupied the same solar system but have lived in different worlds, separated by temperature, by gravity, by their very natures. But celestial mechanics are indifferent to poetry. Orbits are promises written in the unforgiving language of physics, and sometimes they promise a cataclysm. We are about to witness the fulfillment of such a promise, an event so rare and so perfectly aligned, it appears as though the universe itself has conspired to stage a demonstration of its own raw power. This is not a story of a simple collision of rock meeting fire. It is a far more subtle and perhaps a far more terrifying encounter. It is the story of an invisible tempest aimed at a celestial snowflake, a tale of what happens when a star decides to reach out and touch a visitor with a hand of pure, focused energy. To understand the gravity of this impending encounter, you must first unlearn what you think you know about our Sunday. We see it as a constant, a perfect golden disk hanging in our sky, a reliable source of warmth and life. This perception is a life-saving illusion, a comforting fiction granted to us by 150 million kilometers of distance and a protective atmosphere. The truth is a vision of perpetual churning chaos. Up close, the solar surface is not a smooth, serene orb. It is a roiling, seething ocean of plasma, a granulated tapestry of convection cells, each the size of a terrestrial continent, boiling and sinking in a matter of minutes. This is a world where magnetic fields, thousands of times stronger than Earth's, are twisted into colossal, intricate knots by the star's rotation. When these magnetic loops become too strained, they snap. They unleash the energy of a billion hydrogen bombs in a single blinding flash, hurling vast clouds of charged particles out into the solar system. Towering prominences, elegant arches of fire large enough to swallow dozens of Earths, dance for days or weeks before erupting or collapsing back into the stellar furnace. This is our star. It is not a gentle god. It is a titan barely containing an unimaginable rage. And like any titan, it has its moods, its cycles of fury and calm. But even in its quietest moments, it breathes a constant, unceasing wind into space. A stream of protons and electrons boil directly off its million-degree outer atmosphere, the corona. This solar wind travels at a staggering 400 kilometers per second, a relentless outflow that fills the entire solar system, creating a vast bubble of influence we call the heliosphere. It is this wind that strokes the magnetospheres of planets, that ignites the auroras at our poles, and that pushes the tails of comets away from the sun, making them the celestial weather vanes of this invisible current. For the most part, this is the sun, we know, powerful, yes, but its energy diffused, spread out across the immense emptiness of space. But the sun has another face, a darker, more focused, and infinitely more violent potential. And to see it, you cannot look in visible light. You must look through eyes that see the universe in the high-energy wavelengths of extreme ultraviolet. Only then do they appear. Dark, gaping patches on the face of our brilliant star. They look like voids, like regions of utter blackness against the bright textured corona. They are not shadows, they are not sunspots, they are something far more profound. These are coronal holes. They appear dark not because they are cold, but because they are open. In these vast regions, the sun's powerful magnetic field does not loop back down to the surface, creating the elegant arches and intricate structures we see elsewhere. Instead, the magnetic field lines are torn open, unanchored, streaming straight out into the cosmos like the frayed ends of a colossal magnetic cable. They are in effect wounds in the sun's atmosphere. Portals that lead directly from the star's fiery depths to the cold vacuum of interplanetary space. And through these portals, the solar wind does not gently flow. It is violently, relentlessly expelled. This is not the standard 400 km per second breeze. This is a high-speed stream, a solar hurricane of particles, accelerated to more than double that velocity, reaching speeds of over 800 kilometers, sometimes even 1,000 kilometers per second. 2 million miles per hour. A torrent of superheated plasma, a focused directed jet of stellar material fired from the sun like a celestial blowtorch. When one of these streams washes over the Earth, our magnetic shield shudders under the assault. Satellites can be disabled, power grids can be overloaded, and the auroral displays become global spectacular storms of light, a beautiful testament to a planetary defense system pushed to its very limits. A coronal hole is not merely a feature, it is a weapon. It is the nozzle of a cosmic engine of immense destructive potential, and its aim is dictated by the slow, inexorable rotation of the sun itself. For weeks, a coronal hole might spew its fury into empty space, its existence known only to our satellites. But as the sun turns, that nozzle turns with it, sweeping its beam of high-energy particles across the planets like a searchlight. And now that searchlight is beginning to lock onto a new and exquisitely vulnerable target. From the chilling darkness beyond the orbit of Neptune, it has been falling for millennia, a solitary traveler on a journey that began long before human history. Comet 3I Atlas. The name is clinical, a catalogue designation for an object of profound and ancient beauty. It is a time capsule, a loosely packed agglomeration of ice, dust and rock, unchanged since the solar system was a swirling disk of gas and debris 4.5 billion years ago. Deep within its frozen heart, it carries the primordial ingredients of worlds, the very organic molecules that may have seeded life on our own planet. For most of its existence, it drifted within the Oort cloud, the solar system's most distant and mysterious realm, a ghostly sphere of trillions of icy bodies surrounding our sun at a distance of nearly a light year. Here in the absolute zero of interstellar space, it waited. Perhaps the gentle gravitational nudge of a passing star, a subtle cosmic tide, was all it took to dislodge it from its stable, timeless orbit. To send it on a long, slow, irreversible plunge toward the fire at the center of everything. Its journey inward was a slow awakening. For thousands of years it was just a dark, inert rock invisible against the black. As it crossed the orbit of Pluto, then Neptune, the sun was still just the brightest star in its sky. But as it journeyed closer, past Uranus, past Saturn, the distant star began to transform. Its faint warmth started to sublimate the comet's ancient ices, turning them directly from a solid into a gas. A faint ethereal shroud began to envelop the nucleus. A coma. This is the moment a comet is truly born. The sun's radiation pushed on this nascent atmosphere, while the solar wind began to sculpt it, sweeping the dust and ionized gas into two distinct glorious tails. This is the object our telescopes first captured a faint smudge of light on a trajectory that promised a spectacular show. As it continued its inexorable fall, Comet Atlas brightened dramatically, becoming an object of intense interest for astronomers, both professional and amateur. It was on a path that would take it swooping deep inside the orbit of Mercury, a true sungrazer destined for a perilous and fiery close encounter with our star. We have seen comets like this before. We have watched them approach the sun, their tails stretching for millions of kilometers, their icy bodies vaporizing under the intense heat. Some survive their passage scarred and diminished to be thrown back out into the void. Others are not so lucky. They fracture, breaking apart under the immense thermal stress and gravitational forces, their ancient cores dissolving into a trail of cosmic dust. We believed we understood the primary dangers a comet faces, the blistering heat, the crushing gravity. We thought the great celestial drama of Comet Atlas would be this simple elemental battle between ice and fire. We were wrong. The true threat was not the heat. It was not the gravity. It was the wind. Our orbital calculations are precise. They are the bedrock of celestial navigation, allowing us to predict the motions of planets, asteroids, and comets with stunning accuracy. We plotted the path of 3I, Atlas, a graceful sweeping parabola that would carry it around the sun and back out into the darkness from whence it came. Simultaneously, our solar observatories, staring unblinkingly at the sun, were mapping its ever-changing surface. They tracked the birth, evolution, and rotation of its magnetic features, including the monstrously large coronal hole that was beginning to turn into view. And then, as we laid one set of data over the other, a chilling reality emerged. The two paths were set to intersect. This was not a prediction of a physical collision. The comet would still be millions of kilometers from the Sun's surface, but its trajectory was taking it directly into the cosmic firing line. The Sun was slowly rotating, bringing the gaping maw of the coronal hole into alignment. Comet Atlas was accelerating, plunging deeper into the Sun's gravity, well unable to swerve, unable to slow, unable to escape its appointment. The two events, the comet's arrival at a specific point in its orbit and the Sun's rotation bringing the coronal hole to face that exact point, were synchronizing, a celestial alignment of unprecedented scale. For days, perhaps even a week, the comet would not be flying through the normal diffuse solar wind. It would be flying directly into the teeth of a high-speed stream, a focused, unrelenting 2 million mile-per-hour blast of plasma. You must understand what this truly means. A comet is not a solid, impervious rock. Its nucleus is fragile, likely a porous collection of ice and rubble held together loosely. Its primary defense is its own atmosphere, the coma, and the weak magnetic field it generates. This defense works well enough against the gentle pressure of the normal solar wind, creating a beautiful, streamlined structure known as a magnetotail. But what we are about to witness is not a gentle pressure. It is a sustained head-on assault from a particle cannon of stellar proportions. This is a cosmic sandblaster aimed at a delicate crystal. The questions this alignment poses are as profound as they are terrifying. What happens to a comet's atmosphere when it is struck by a force hundreds of times more powerful than what it is designed to withstand? Will the high-speed stream simply blow the coma away, stripping the nucleus of its protective, gaseous shield in a process known as cometary death? If the nucleus is exposed, raw and unprotected, to the full direct fury of the Sun, will the thermal shock be enough to shatter it instantly? Could the sheer kinetic energy of the plasma stream, this hurricane of protons and electrons, physically erode the nucleus, tearing it apart piece by piece? Or is it possible that comets, these ancient survivors, are more resilient than we imagine? Could this unprecedented event reveal some unknown mechanism, some hidden strength in the structure of these icy wanderers? We have theories, we have models, but we have never seen this happen before. Never with such a perfect alignment, with such a well-observed comet, and with a coronal hole of this magnitude. We are about to move from the realm of academic speculation into the stark reality of direct observation. The universe is offering us a front-row seat to an extraordinary experiment, one that we could never hope to replicate. The results will have profound implications, rewriting our understanding of the relationship between our star and the fragile bodies that drift through its domain. It will teach us about the true power hidden within the Sun, the focused ferocity that is usually directed out into the cosmic emptiness. And it will tell us the ultimate fate of these celestial ghosts, these messengers from the past, when they fly too close to the fire. The stage is set, the actors are moving into position. A star is taking aim, and a comet, after a journey of 1 million years, is about to fly directly into the storm. Is it possible for the universe to conspire, for events separated by billions of miles and millions of years to converge with the precision of a clockwork mechanism? We live our lives comforted by the illusion of cosmic indifference, by the mathematics of probability that tell us a falling star is just a rock and its path is merely a testament to gravity. But what if we were to witness a pattern so uncanny, so strangely orchestrated, that it forced us to question the very nature of cause and effect across the solar system? What if a forgotten messenger from the dawn of time was found to be on a collision course, not with a planet, but with a storm A, storm of unimaginable power born from the very heart of our star? This is the story of a celestial alignment that should not be possible, a silent conversation between a star's fury and a comet's fragile journey. To understand the strangeness of this encounter, you must first reimagine the star you think you know. The Sun, our Sun, is not the serene, perfect orb of childhood drawings. It is a place of breathtaking violence. We see it as a source of gentle warmth, but to look upon its surface is to witness an ocean of incandescent plasma, churning and boiling at scales that dwarf our world. Its surface is a tapestry woven from magnetic forces so powerful they could crush a planet, a constant raging battlefield of creation and annihilation. This is a star in its chaotic prime, and its influence extends far beyond the light that reaches our sky. It projects a presence, a physical and energetic bubble that envelops every planet, moon, and asteroid in our system. This sphere of influence, the heliosphere, is the Sun's kingdom, and it is governed by the star's ever-changing moods. And to truly grasp its power, we have to look not at its brilliant face, but into the ethereal, ghostly halo that surrounds it, the corona. Here, in this wispy, superheated atmosphere, one of the most profound paradoxes in modern astronomy unfolds. The visible surface of the Sun, the photosphere, burns at a staggering 6,000 degrees Celsius. Yet as you move away from it into the tenuous corona, the temperature doesn't drop, it skyrockets. It explodes to over 1,000,000 degrees, 1,000 times hotter than the fiery furnace below. This impossibly hot, ghost-like aura remains a deep and persistent puzzle, a flagrant violation of our everyday intuition. It's like stepping away from a bonfire, only to find yourself incinerated by a blast of heat 100 feet away. For decades, we have sought the hidden engine driving this incredible superheating, proposing everything from magnetic waves to storms of nanoflares. The corona is where the Sun's raw power is refined, transformed into a weapon that it wields against the cosmos, and it is from here that the solar wind is born. This is not a wind in any terrestrial sense. There is no air, no gentle breeze. It is a relentless, unending hurricane of charged particles, protons, electrons, the very building blocks of matter, ejected from the Sun and accelerated to phenomenal speeds. This solar wind streams outwards in all directions, a constant exhalation that travels through the vacuum of space, sculpting the magnetic fields of planets and carving the tails of comets. Most of this wind is a relatively gentle, though still formidable, flow. But the Sun has another far more violent mode of expression. Its magnetic field, the invisible architecture that governs its every eruption and flare, is not uniform. In most places, it loops back upon itself, creating enormous, elegant arches of trapped plasma, rising and falling in a fiery ballet. These closed loops act as magnetic cages containing the star's fury. But in certain regions, something different happens. The magnetic field lines do not loop back, they break. They snap open like a severed power line and stream directly out into the void of interplanetary space. These regions, when viewed in the extreme ultraviolet light that reveals the corona's structure, appear as dark, gaping voids against the brighter, hotter surroundings. They look like chasms, like holes in the Sun's atmosphere. We call them coronal holes. This darkness is deceptive. They are not cold or empty. They are dark only because the superheated plasma that should be trapped there is not. It is escaping. These holes are the nozzles of a celestial blowtorch. They are portals through which the Sun unleashes its most ferocious energy, funneling out high-speed streams of solar wind that can travel at over 2 million miles per hour. A torrent of particles, a river of energy blasting out from the star with focused directional intensity. For life on Earth, our planet's own magnetic field acts as a shield, a deflector that channels this solar fury towards the poles, giving us the sublime beauty of the aurora. But for a defenseless object caught in its path, a direct hit from one of these streams is a catastrophic event. And for decades, these solar features were just that, a fascinating, powerful aspect of our star's behavior, a matter for solar physicists and space weather forecasters. They were the Sun's business. Until a new traveler arrived, and its path began to intersect with these invisible rivers of fire in a way no one had anticipated. Out in the cold, dark frontier of our solar system, far beyond the orbit of Neptune, lies a theoretical realm of unimaginable size. The Oort cloud. It is a vast spherical shell of icy bodies, trillions of them, the leftover debris from the formation of the planets 4.5 billion years ago. They are the solar system's deep freeze, a cosmic attic filled with pristine primordial relics. Here in the near absolute zero of interstellar space, they drift in a darkness so profound the Sun is just the brightest star in the sky. For eons, they remain in a state of gravitational equilibrium, barely tethered to our star's influence. But sometimes something disturbs this delicate peace. The gravitational nudge from a passing star, a jostle from the galaxy's tidal forces is all it takes. A single one of these icy bodies can be dislodged from its ancient orbit and sent on a long, slow, final journey, a fall that can last for millions of years towards the inner solar system, towards the furnace. In the final days of 2019, an automated survey designed to scan the heavens for potential threats to Earth, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, flagged a faint, fuzzy smudge of light moving against the background of distant stars. This is how most modern discoveries are made, not with a human eye peering through an eyepiece, but with a silent, tireless robotic sentinel running sophisticated algorithms. At first, it was just another data point, another faint object to be catalogued. But as observatories around the world turned their attention to it, a thrill of excitement began to ripple through the astronomical community. This was no ordinary asteroid. As it drew closer to the Sun, its surface of ancient ice began to warm, transforming directly from a solid into a gas in a process called sublimation. This process was creating a vast, glowing atmosphere around its tiny nucleus, a coma, and the pressure from the solar wind was beginning to push this material into a ghostly tail. It was a comet, a magnificent long-period comet hurled inwards from the deepest reaches of space. It was given the designation 3I, Atlas. The eye hinted at its mysterious origins, a potential interstellar visitor, though its trajectory was more consistent with a native of the Oort cloud. But its pedigree was less important than its performance. The comet was brightening at a dramatic, almost unprecedented rate. With each passing week it grew more brilliant. Astronomers began to make breathless predictions. Could this be it? Could this be the one they had been waiting for? A great comet, an object so luminous it would be visible to the naked eye, a spectacular apparition gracing our evening skies. The public imagination was captured. This lonely wanderer, this time capsule from the birth of our world, was coming home in a blaze of glory. It became a symbol of hope and wonder in a world grappling with uncertainty. Every new image revealed more detail, a beautiful green coma glowing with diatomic carbon and a tail stretching for millions of miles. Its path was meticulously calculated, a graceful arc that would carry it inside the orbit of Mercury, bringing it perilously close to the Sun in May of 2020. This proximity was the source of its anticipated brilliance, the solar heat acting as a celestial engine driving its spectacular outgassing. But this closeness was also the source of its peril. And that is when a few sharp-eyed solar scientists, the ones who spend their lives watching the Sun's every breath and tremor, began to notice something. It was subtle at first, a detail buried in the complex orbital mechanics and the dynamic maps of the Sun's corona. It wasn't a single event, but a dawning realization, a strange and repeating correspondence in the data. While the comet watchers were looking up at Atlas, the solar watchers were looking at the Sunday. They were tracking the birth, evolution, and rotation of the coronal holes, the open wounds in the Sun's atmosphere. These holes can persist for weeks, sometimes months, rotating with the Sun like the nozzle of a gigantic sweeping sprinkler system. And as they cross the face of the Sun, they spray their high-velocity solar wind streams out into the solar system. Using data from a fleet of solar observatories, they could model the path of these streams, predicting with remarkable accuracy when they would wash over Earth or any other point in space. Someone decided to overlay the two data sets, the meticulously plotted trajectory of Comet 3I, Atlas, and the projected spiraling paths of the high-speed solar wind streams emanating from the Sun's most active coronal holes. What they saw was startling. It was more than a coincidence. It was a persistent, recurring alignment. The comet wasn't just flying towards the Sunday. Its inbound path was leading it directly into the firing line of not one, but a series of potent geo-effective coronal holes. As the Sun rotated, it was as if it were taking aim. Each time a significant coronal hole was set to rotate into a position facing the inner solar system, the comet's trajectory would days later carry it precisely through the subsequent particle stream. It was scheduled to fly through the cosmic equivalent of a hurricane, then another, and then another. The chances of a single such intersection were low. For it to happen repeatedly with multiple distinct solar features was statistically improbable. A question began to form in the quiet corners of research labs and online forums, a question that was at once absurd and deeply compelling. Was the comet's path somehow linked to the sun's activity? The notion itself flew in the face of established physics. The sun's magnetic activity is a product of its own internal dynamo, a process of immense complexity that should have absolutely no connection to the gravitational trajectory of a small, icy body billions of miles away. A comet's path is governed by the elegant, predictable laws of gravity laid down by Newton and refined by Einstein. It is a dance with the sun's mass, not with its magnetism. The two phenomena were supposed to be completely independent ships passing in the cosmic night, yet the data was undeniable. A pattern had emerged, a strange and unsettling resonance between the star and the visitor. It was as if this ancient relic, after a slumber of 4 billion years, had awoken and chosen a path not of least resistance but of maximum confrontation. We were about to witness what happens when a fragile ghost from the past flies directly into the heart of a solar storm, and no one could truly predict what would happen when the first blast finally struck. And so the vigil began. Across the planet, a network of eyes, both human and robotic, turned its gaze inward, tracking the silent fall of 3I, Atlas, toward the heart of our solar system. The initial thrill of discovery, that electric moment of finding a new wanderer among the stars, had matured into something deeper, something far more urgent. It was no longer a matter of simply charting a path. It was about bearing witness to an impending and perhaps unprecedented cosmic confrontation. Every day the comet grew in our viewfinders, transforming from a faint ethereal smudge into a defined entity with a burgeoning coma of vaporizing ice and dust, a ghost becoming flesh. From the high, arid plains of the Atacama to the frozen peak of Mauna Kea, and out into the lonely vacuum of space, where our most powerful observatories drift, a singular focus had taken hold. The data streams became torrents, flooding servers with petabytes of information, spectral analyses, photometric readings, and astrometric measurements of exquisite precision. This obsessive watch was fueled by a dawning and deeply unsettling realization. The comet's trajectory, calculated and recalculated with ever-increasing accuracy, was no longer just an elegant arc governed by gravity. It was a timeline. It was a countdown. We could now see with chilling certainty that its path would intersect a region of space that was, for all intents and purposes, the barrel of a loaded gun. The sun, our placid, life-giving star, was turning. As it rotated on its axis, vast dark chasms in its corona, those mysterious voids we call coronal holes, were swiveling into position. These were not mere sunspots or fleeting flares. They were gaping wounds in the solar atmosphere regions, where the sun's magnetic field, instead of looping back on itself, was torn open, streaming directly out into the void. They were unfettered gateways, and through them the sun was exhaling a storm. Our models, the sophisticated computer simulations that had served us so well for decades, painted a clear, if dramatic, picture of what to expect. This high-speed solar wind, a relentless gale of protons and electrons screaming away from the sun at over 2 million miles per hour, would act as a celestial sandblaster. As 3I, Atlas, entered this stream, this hypervelocity river of plasma, the encounter should have been a textbook case of solar cometary interaction magnified to an awesome scale. We expected the comet's tenuous atmosphere, its coma, to be violently sculpted. We anticipated the creation of a spectacular ion tail, a streamer of fluorescing gas molecules stripped of their electrons and captured by the solar wind's magnetic field, pointing like a luminous finger directly away from the sunday. We predicted the dust tail, composed of heavier particles, would curve gracefully behind it, a pale, sweeping train tracing its orbital path. It was to be a magnificent, violent, yet ultimately understandable ballet of physics, a testament to the sun's overwhelming power and the comet's fleeting resilience. The first hint that our predictions were not just wrong but profoundly inadequate came not as a sudden cataclysm, but as a subtle flicker in the data, a whisper of dissent against the chorus of our expectations. It began with the light. Astronomers measuring the comet's brightness, a routine process known as photometry, started reporting anomalies. Comets by their nature are fickle beasts. As they warm, pockets of volatile ice can sublimate explosively, causing them to flare in brightness for a few hours or days. These outbursts are normal, expected, but this was different. 3I, Atlas, wasn't just flaring, it was pulsing with an unnatural rhythm. Its brightness would surge by a factor of 10, then 20, far exceeding what could be explained by simple outgassing. The surges were too sharp, the peaks too high, and the subsequent dimming too erratic. It was as if we were watching a firefly sending a panicked, incoherent signal from the depths of space. The light curves, those elegant graphs of brightness over time, looked less like the gentle hills of cometary activity and more like the jagged, chaotic readouts of a seismograph during an earthquake. Frantic emails crisscrossed the globe between observatories. Was it an instrument calibration error? A flaw in the processing software? Teams in Chile cross-checked their results with teams in Hawaii, who then conferred with analysts processing data from Hubble. The conclusion was inescapable. The instruments were sound. The data was real. The comet itself was behaving erratically, shimmering with a strange, feverish light that defied easy explanation. The simplest models of solar heating were failing, and failing spectacularly. The sun's light was warming the comet, yes, but something else, something unseen and immensely powerful, was agitating it, making it shine with a borrowed and violent glory. The mystery deepened when high-resolution images began to resolve the comet's magnificent tail structure, or rather, its increasingly bizarre lack of structure. The clean, beautiful dichotomy we expected, the straight blue ion tail and the curved white dust tail, was dissolving into chaos. The ion tail, which should have been a well-defined coherent streamer, was frayed and shredded as if it had passed through a celestial briar patch. It appeared kinked and violently twisted, snapping back and forth in the solar gale, with a speed that shocked even the most veteran observers. It was no longer a graceful pennant, it was a tattered flag in a hurricane. This wasn't the steady pressure of the solar wind we knew. This was a turbulent, ferocious assault. The plasma river was not flowing. It was a torrent filled with eddies and whirlpools of magnetic energy, tearing at the comet's gaseous envelope with unimaginable force. Then a new feature emerged, one that had no place in our textbooks. Between the ion and dust tails, a third ghostly appendage began to form. It was a faint, diffuse fan of material composed of neutral sodium atoms ejected at an angle that made no physical sense. This sodium tail, as it was quickly dubbed, was a spectral enigma. For sodium to be liberated from the dust grains in the coma and then pushed away from the sun with such velocity required an energy input that was simply off the charts. The sunlight alone was not enough. Some other process, some incredibly efficient and violent mechanism was at work, acting like a celestial blowtorch that was not merely melting the comet's surface, but atomizing it, blasting its very substance apart particle by particle. The sun wasn't just pushing the comet's atmosphere, it was actively disassembling it, revealing a level of interaction that felt less like physics and more like a targeted attack. We were seeing the signature of a force more potent and more destructive than we had dared to imagine. The cascade of anomalies continued, each one more alarming than the last. While visual and spectral data told a story of external chaos, it was the application of advanced radar astronomy that delivered the most chilling revelation of all. By bouncing powerful radio signals off the comet's nucleus from the Arecibo and Goldstone antennas, scientists could pierce through the obscuring veil of the coma and glimpse the solid body within. What they found turned a scientific puzzle into a genuine crisis. The nucleus, a mountain of ice and rock perhaps 10 kilometers across, was not intact. The radar echoes, when painstakingly reconstructed into three-dimensional models, revealed a network of fine, spidery lines crisscrossing its surface. Hairline fractures, the beginnings of a catastrophic structural failure. This was the terrifying linchpin that connected all the other strange phenomena. The erratic, pulsing brightness was suddenly recontextualized. It wasn't just gas bursting from vents. It was the brilliant, mirror-like flash of pristine crystalline ice being exposed to sunlight for the first time in 4.5 billion years as new cracks propagated across the nucleus. The violent shredding of the ion tail and the inexplicable sodium streamer were symptoms of the same underlying trauma. The comet wasn't just shedding its atmosphere, It was being physically broken. Small fragments, perhaps the size of cars or houses, were being spalled from the surface, instantly vaporizing in the solar onslaught and feeding the bizarre tales with a fresh supply of ionized and atomized material. A dreadful synthesis began to form in the minds of researchers huddled in late-night teleconferences, their faces illuminated by the glow of data-filled screens. This was not a normal comet encountering a normal solar wind. Comets disintegrate, of course. They are fragile relics. But their demise is typically driven by the immense tidal forces experienced during a close pass of a planet, or the sun itself, or through thermal stress that cleaves the nucleus apart as it roasts near perihelion. 3I, Atlas, was still tens of millions of miles from that point of maximum danger. It was being shattered prematurely far out in what should have been relatively safe space. The inescapable conclusion was as simple as it was terrifying. The solar wind being spewed from these specific aligned coronal holes was fundamentally different. The models had to be thrown out. This was not the familiar solar breeze. This was something else entirely. Hypotheses flew, each more radical than the last. Was this a stream of solar wind that was orders of magnitude denser than any we had ever recorded? Was it moving at a velocity that bordered on the relativistic? Or perhaps most disturbingly, did it carry a bizarre and complex magnetic field, structure a tangled knot of magnetic flux ropes that were acting like a gravitational whip, lashing the comet and inducing powerful electrical currents that were cracking its nucleus from the inside out? We were witnessing the sun's ability to exert not just pressure but a direct kinetic shattering force across vast distances of space. The line of fire was real, but the ammunition was something new and utterly unknown. We were no longer just observers of a celestial passage. We had become unwilling spectators at a public execution. The comet, this ancient messenger from the interstellar dark, had survived a journey of millions of years, a trek through the cold, empty gulfs between the stars, only to arrive in our backyard and face a form of stellar aggression for which we had no precedent. Every anomalous photon, every distorted magnetic field line, every newly mapped fracture on its dying heart told the same story. We were profoundly underestimating the power and the complexity of our own star. As 3I, Atlas plunged deeper into that invisible torrent, a stark realization settled upon the scientific community. We were sailing into uncharted territory. Our maps were useless, our compass was spinning wildly, and ahead of us in the blinding glare of the sun, a storm of unimaginable proportions was just beginning to rage. We could only watch and wait and wonder what would be left of the traveler when it finally emerged from the other side. And so, we waited. For days the world's observatories held their collective breath, their great electronic eyes trained on that one specific lonely patch of sky. The predictions from Act 2, those elegant but terrifying lines of code, had foretold a moment of truth. They spoke of an invisible collision, a confrontation between an ancient icy wanderer and a phantom force flowing from the sun's own ghostly canyons. The theoretical models had warned of it, the simulations had hinted at the possibility, but no one was truly prepared for the savage reality that was about to unfold across millions of miles of vacuum. What the relentless stream of data finally painted on their screens was not the elegant portrait of a comet they had anticipated, but a visceral, shocking tableau of cosmic demolition. It began not with a bang, but with a flicker in the high-resolution images, a subtle, almost imperceptible change in the comet's shape. At first, it looked like a photographic artifact, a digital ghost in the machine. The usually crisp, defined edge of the comet's nucleus, the solid heart of this celestial pilgrim, appeared frayed, blurry. As subsequent images cascaded in minute by minute, the blur resolved itself into something far more alarming. We were witnessing fine, gossamer threads of material being pulled away from the main body, not in the gentle fan-like tail we expect, but with a violent, tormented energy. It was as if an unseen hand had reached across space and was carding the comet like raw wool, tearing at its very substance. This was not the gentle sublimation of ice into gas that gives a comet its beauty. This was a brutal act of physical violation, a scouring. The initial wonder in control rooms across the planet quickly turned to a hushed, disbelieving awe. The alignment was not just a curiosity, it was a kill zone, but the full, horrifying truth of the event would not be revealed by pictures alone. For that, we had to turn to a different kind of light, to the forensic science of spectroscopy. By splitting the faint light from 3I, Atlas, into its constituent rainbow of colors, astronomers can read its chemical fingerprint, identifying the specific atoms and molecules present. The initial spectra were exactly as predicted signatures of water vapor, carbon monoxide, and dust, the standard building blocks of a cometary core. Yet, as the comet plunged deeper into the solar wind stream, the spectrographs began to scream. New signatures, new elemental ghosts began to appear in the data with an intensity that stunned the teams on the ground. These were not the elements that gently boil off a comet's surface. We saw the spectral lines for sodium, then magnesium, and even iron flaring into existence. These are heavier elements, locked deep within the silicate rock and dust that form the comet's structural foundation. To see them in the coma, the gaseous atmosphere surrounding the nucleus, meant that something was not just melting the surface ice, but was physically blasting away the rock itself. It was the equivalent of watching a gentle breeze suddenly gain the force to strip brick from a wall. The solar wind, focused and accelerated by the magnetic funnels of the coronal holes, had become a celestial blowtorch. It was no longer merely pushing on the comet's atmosphere, it was atomizing its very body, chipping away at the primordial rock that had remained frozen and untouched since the birth of the planets. The data was unequivocal, a death warrant written in the language of light. And the velocities were staggering. Using the Doppler effect, the same principle that makes an ambulance siren change pitch as it passes you, astronomers could measure the speed of this escaping material. The gases were not drifting away, they were being violently ejected. We clocked debris moving at hundreds of kilometers per second, flung away from the nucleus with such force that it would never return. This was not a comet shedding its skin. This was a body hemorrhaging its lifeblood into the void. Each particle of rock, each molecule of ancient ice was a piece of history, a 4.5 billion-year-old message in a bottle, and we were watching it all be shredded into an illegible storm of cosmic shrapnel right before our eyes. The sheer volume of material being lost was orders of magnitude greater than any model of normal cometary decay could possibly account for. The sun wasn't just influencing 3I, Atlas, it was actively unmaking it. The high-resolution images now viewed with this new terrifying understanding became a chronicle of a world being torn apart. What was once a single solid nucleus began to resolve into a chaotic swarm. A large fragment, perhaps a kilometer wide, sheared off from the main body, tumbling wildly as it was instantly assaulted by the same furious stream of particles. As it spun, fresh, unshielded ices were exposed to the solar onslaught, erupting in brilliant, silent explosions of gas and dust. These new jets acted like thrusters, sending the fragment into an even more erratic spin, ensuring its own rapid destruction. It was a chain reaction of disintegration. The comet was carving icebergs of rock and frozen gas, each one a new target, each one contributing to the rapidly expanding cloud of debris. You could see the battle lines drawn in the cosmos. On one side, the ancient cohesive gravity of a body that had held itself together on a journey of millions of years. On the other, the relentless focused fury of its parent star. And gravity was losing. The stream from the coronal hole was a focused beam of kinetic energy, a continuous percussive blast against the comet's fragile structure. Every microscopic crack, every geological fault line from some long-forgotten impact was now a weakness to be exploited. The solar wind particles, streams of protons and electrons, were not just flowing past the comet. They were penetrating these fissures, pressurizing them from within, and prying the entire structure apart, piece by agonizing piece. The grand and beautiful object that had captivated our attention for months was being reduced to rubble. We were no longer observing a comet. We were watching the birth of a meteor stream, not over the course of millennia, but in a compressed, grotesquely accelerated time frame of mere days and hours. The single point of light was transforming into an elongated, ghostly smear across the sky. This was profoundly different from other famous cometary destructions. When Comet Shoemaker Levy 9 was torn apart, it was by the colossal gravity of Jupiter. a brutal but understandable gravitational execution. Other comets have simply fizzled out, their volatile ices exhausted after too many trips around the sun, fading quietly into dark asteroids. But this was new. This was a death by 1,000 cuts, administered by a force we had always seen as a background presence, not a precision weapon. It was a testament to the fact that even in our own solar system, in our own backyard, there are forces at play we have profoundly underestimated. The emotional shift among the scientific community was palpable. The initial thrill of discovery had been replaced by a kind of somber, clinical urgency. This was no longer just a target of opportunity. It was a cosmic crime scene. Every available telescope that could be brought to bear was retasked. The Hubble was commanded to stare unblinking. Ground-based observatories from Chile to Hawaii initiated target of opportunity protocols, dropping their scheduled observations to join the vigil. Radio telescopes strained to listen for the faint hiss of interacting plasma fields, while infrared arrays searched for the thermal glow of the newly liberated dust. It became a frantic global effort to document every moment of the comet's final agony, to capture every photon from this unprecedented spectacle of celestial destruction. We were learning in real time just how vulnerable these visitors from the outer darkness truly are. A comet is a delicate balance of gravity and ice, a loosely bound collection of primordial dust and frost. For eons, 3I, Atlas, had survived the deep freeze of interstellar space, the subtle gravitational nudges of distant stars, and the lonely trek through the Kuiper belt. It had endured for ages in the quiet stillness of the outer solar system. But here, in the inner sanctum, the rules were different. The sun, the very star that illuminates and gives life, had revealed another face, that of an executioner. The coronal holes, once seen as mere curiosities in the sun's atmosphere, had proven themselves to be potent engines of cosmic change, capable of dismantling an entire world with a focused, unrelenting stream of invisible particles. And as the nucleus continued to fracture, a profound realization began to dawn. The comet itself was almost a secondary character in this story now. The main event was the aftermath. The beautiful, coherent tale was gone, replaced by a vast, chaotic, and expanding cloud of debris. This was no longer a single object on a predictable path. It was now a diffuse river of rock and ice, millions of kilometers long, a brand new feature being painted directly onto the map of the inner solar system. Each fragment, from the finest dust to the largest mountain-sized chunks, was now on its own, slightly different trajectory, a new variable in the complex gravitational dance of the planets. The spectacular death of 3I, Atlas, was not an ending. It was a transformation. It was creating a hazard, a potential minefield being laid down in the very space through which our own planet travels. The sight was magnificent, a shimmering, expanding ghost of a world that once was a celestial autopsy playing out on the grandest of scales. But woven into that terrible beauty was a new and unsettling question, a question that hung in the silence of every control room and observatory on Earth. We were watching the comet die, yes, but its death was giving birth to something new, something unpredictable. The question was no longer if times the comet would survive the encounter, for we now knew with absolute certainty that it would not. The urgent, pressing question, the one that would set the course for the next phase of our investigation, had become far more personal and far more frightening. What would its spectacular demise now unleash upon us all? The spectacle is over. The silent celestial firework that was 3I, Atlas, has faded, leaving behind not a triumphant survivor, but a ghostly funeral procession of ice and dust. In the aftermath of its cataclysmic disintegration, we are left staring into the void, confronted not with an answer, but with a far more profound and unsettling question. We saw the comet die, we watched it surrender its form to the inexorable forces of the inner solar system. But the true perpetrator wasn't merely the sun's heat, that familiar and predictable executioner of icy wanderers. No, the evidence trail, written in faint streams of gas and captured in the cold data of our telescopes, points to a different kind of killer. An invisible directed force, a phantom wind unleashed from the sun itself, which turned what should have been a close pass into a complete and utter annihilation. The crime scene is vast, stretching for millions of kilometers, and our forensic tools are observatories on Earth and in orbit. Sifting through the spectral light of the comet's remains, scientists began to reconstruct the final fatal moments. They had tracked the coronal hole, that dark, ominous patch in the sun's outer atmosphere, for days. They knew it was rotating into position, aimed like the barrel of a cosmic cannon directly along the comet's path. The predictions were for a harsh encounter, a buffeting that might shear off some material or brighten its tail. But no one, not in their most extreme models, predicted this. This was not a simple erosion. It was a demolition. It forced us to look again at the solar wind, not as a constant gentle breeze, but as something capable of focused, overwhelming violence. Imagine standing on a beach, feeling the sea air on your face. That is our typical conception of the solar wind here on Earth, shielded as we are by our powerful magnetic field. Now, imagine that breeze is replaced by the full directed blast of a fire hose, one that isn't firing water but a plasma of charged particles traveling at over 1,000,000 miles per hour. This is the reality a naked comet faces when it crosses the stream of a coronal hole. Each particle, a single proton or electron, is a microscopic bullet. Alone, it is insignificant. But arriving in a torrent of 100 billion particles per square inch every second, their collective impact becomes a relentless kinetic force, a form of celestial sandblasting on a scale that defies earthly comparison. This constant, brutal pressure began to act like a physical hammer on the comet's nucleus. 3I, Atlas was not a solid cannonball of rock. Like most comets, it was a fragile agglomerate of ice dust and frozen gases, likely held together with the structural integrity of a loosely packed snowball. As the solar wind intensified, the kinetic energy transfer was immense. It wasn't just melting the surface, it was imparting physical momentum, creating vibrations and stresses deep within the comet's core. Tiny fractures born in the deep freeze of the outer solar system over billions of years would have begun to propagate. The entire structure started to shudder, to resonate with the force of the plasma storm raging around it. The sun's heat was already turning its outer layers into vapor, weakening the bonds that held it together. But this kinetic onslaught was the jackhammer shaking the building's very foundation while it was already on fire. Yet even this, the sheer brute force of the particle stream, wasn't enough to explain the catastrophic speed of the breakup. The disintegration was too rapid, too complete. There was another, more insidious weapon at play, one that attacked the comet not from the outside in, but from the inside out. To understand it, we have to look beyond the physical particles and see the invisible architecture they carry with them, the interplanetary magnetic field. The solar wind is not just a stream of matter, it is a magnetized plasma. It carries the sun's own magnetic field outward, stretching it through the solar system in a complex spiraling pattern. Atlas II had its own defense, a miniature magnetic bubble called a magnetosphere, generated by the interaction of the solar wind with its own outgassing coma. For a brief time, this bubble, this cometary shield, held. It was a tiny, ephemeral outpost of order against the chaos of the sun's gale. But the magnetic field streaming from the coronal hole was different. It was simpler, more open, a direct line of magnetic force pointing straight out from the Sunday. As this powerful unipolar field washed over 3I, Atlas, it encountered the comet's own complex draped magnetic field lines. And here, in the silent clash of invisible forces, the true tipping point was reached. The phenomenon is known as magnetic reconnection, and it is one of the most explosive events in the universe. You have to imagine it not as a collision, but as a catastrophic short circuit on a cosmic scale. When two magnetic field lines with opposite polarities are pushed together, they don't just bend around each other, they can break and in an instant violently reconfigure into a new, simpler shape. The energy that was stored in maintaining those complex, stressed magnetic fields has to go somewhere, and it is released in a sudden, explosive burst of pure energy. This is what happened in the coma of 3I, Atlas. As the sun's magnetic field lines pressed in, they found their opposites in the comet's own defensive bubble. A fatal connection was made. All around the comet, countless magnetic short circuits began to fire off, unleashing tremendous energy directly into the gas and dust of the coma. The effect was immediate and devastating. The comet's atmosphere was superheated in a flash, ionized and stripped away with a violence far exceeding the steady push of the solar wind. It was like detonating a series of depth charges around a submarine. The shield didn't just fail, it was turned into a weapon against the very body it was meant to protect. This magnetic storm ripped the coma to shreds, exposing the fragile, naked nucleus beneath to the full, unmitigated fury of the kinetic bombardment. The 1-2 punch was complete. Stripped of its atmospheric armor, the nucleus, already shuddering from internal stresses, finally gave way. It did not just break into a few large pieces, it shattered. It crumbled into an expanding cloud of cosmic dust and frozen gravel who its ancient heart silenced forever. The death of 3I, Atlas, was not just a tragic spectacle. It was a profound scientific revelation, a moment that forces us to re-evaluate the very nature of our solar system. We have been forced to tear up the old rulebook on cometary survival. For decades, our models were dominated by gravity and thermodynamics. We calculated how close a comet could get to the sun before its ices sublimated too quickly, before tidal forces pulled it apart. We treated the sun as a giant, predictable furnace. Now we know it is also a capricious magnetic dragon. The survival of a comet, we have discovered, may have less to do with its composition and more to do with the invisible turbulent weather of the space it travels through. An entirely new field of cometary forecasting is being born, one that must account for the sun's ever-changing magnetic temperament. This discovery ripples outward, touching every corner of solar system science and posing a host of daunting new questions. How many times has this happened before? We have long been puzzled by so-called asteroid belts in strange comet-like orbits, places where we would expect to find ice, not rock. Could it be that we are not looking at primordial fields of asteroids, but at the graveyards of comets that suffered the same fate as Atlas, their volatile ices sandblasted away over eons by less intense but equally persistent solar winds? Are we fundamentally misinterpreting the history of our solar system, mistaking the victims of solar storms for its original inhabitants? The ghost of Atlas suggests this is a chilling possibility we must now seriously consider. The implications for the future are even more staggering. We are entering an age of unprecedented exploration, sending probes and eventually humans deeper into the solar system. We now understand that a coronal hole stream is not just a radiation hazard, it is a physical threat. A spacecraft, resilient as it is, could be eroded. Delicate instruments could be damaged by the sheer kinetic force of the plasma. For a fragile, inflatable habitat on Mars, or a temporary base on the Moon, such an event could be catastrophic. We have learned to forecast space weather to protect our satellites in Earth orbit, but now we must learn to forecast it for every potential pathway a mission might take through the vast emptiness between the planets. The solar system, it seems, has a hidden layer of violent weather patterns we are only just beginning to chart. And what of visitors? In recent years, we have been graced by the arrival of interstellar objects like Oumuamua and Borisov messengers from other star systems passing through our own. These travelers face a unique gauntlet. They pass through our sun's domain only once on a trajectory that offers no second chances. How would a fragile alien object, perhaps constructed differently from our own comets, react to a direct hit from a coronal hole stream? We saw Oumuamua exhibit a strange non-gravitational acceleration as it left our system a tiny push that astronomers struggled to explain. While outgassing from unseen ices remains the leading theory, the encounter with Atlas forces us to ask, could Oumuamua have experienced a glancing blow from a solar wind stream, a magnetic interaction that gave it a slight, almost imperceptible nudge on its way back into the interstellar dark? It is a tantalizing, almost untestable idea, but one that highlights how profoundly our understanding has been shaken. We are no longer just passive observers of these passers-by. We are hosts in a solar system that is at times dangerously inhospitable. This single event has thrown the scientific community into a state of frenetic reappraisal. Old data from past comets is being re-examined with fresh eyes. Were there signatures of magnetic reconnection that we missed? Did the unexpected fizzling of other promising comets have a cause we failed to recognize at the time. Supercomputer models are being frantically rewritten, coded with the complex physics of magnetohydrodynamics, attempting to simulate the SMI, fatal dance between a comet's coma and the sun's magnetic field. What was once a relatively simple calculation of orbital mechanics and heating has become a multivariable problem of terrifying complexity. We need to know the comet's trajectory, its rotation, its composition, the strength of its outgassing, and now we need a precise forecast of the sun's magnetic activity along every single point of its future path. Predicting which comet will survive and which will perish has suddenly become exponentially harder. It is like trying to predict the fate of a paper boat in the ocean. You can know the boat's design and the direction of the major currents, but you can never truly know when a rogue wave born of complex forces far from shore will rise up and swamp it in an instant. The sun's coronal holes are those rogue waves. They are a fundamental yet unpredictable feature of our star's existence. The destruction of 3I Atlas was not an anomaly, it was a warning. It was the solar system reminding us that for all our knowledge, for all our powerful telescopes and sophisticated models, we are still just beginning to comprehend the intricate and sometimes violent rules that govern our own cosmic neighborhood. The comet's death has illuminated a hidden danger, and now, as we push further out into this brilliant and treacherous space, we must learn to navigate it with a new and deeper respect for the star that gives us life, but also possesses the power to destroy. And so the case file lay open on the desks of humanity. The evidence was all there, gathered from every corner of our ingenuity. We had the eyewitness accounts from earthbound telescopes charting the comet's fading heartbeat in cold, hard numbers. We had the spectral forensics from Hubble and Spitzer analyzing the chemical ghost of 3I Atlas as it dissipated. We possessed the solar surveillance from SOHO and the Solar Dynamics Observatory, their unblinking eyes fixed upon the sun's churning, violent surface. And most crucially, we held the data from our emissary in the Inferno, the Parker Solar Probe, which had physically tasted the solar wind, measuring its velocity, its density, its temperature, its very soul. The pieces of the puzzle were scattered before us, a cosmic mosaic in disarray. The alignment was undeniable, the timing impossibly coincidental. But in science, correlation, no matter how compelling, is not causation. A grand jury of astrophysicists could see the motive and the opportunity, but they lacked the final, irrefutable proof, the smoking gun. They needed to reconstruct the crime scene not in a laboratory but inside a universe of their own making. They needed to build a digital twin of this entire intricate solar system, a perfect echo in silicon of that fateful encounter in the spring of 2020. The task was monumental, a challenge thrown down to our most powerful machines. At centers of high-performance computing across the globe, digital titans humming with the quiet fury of controlled lightning were awakened and given their sacred charge. Their mission to ingest every last byte of observational data, every photon captured, every particle measured, and from this raw material to spin a virtual cosmos so accurate it would be indistinguishable from reality. This was not merely an animation, it was a resurrection. The first step was to build the stage. Programmers and physicists worked in concert, laying down the fundamental laws. The unyielding bedrock of gravity was coded first, dictating the elegant clockwork dance of the planets and the comet's own trajectory. Every gravitational nudge from Jupiter, every subtle pull from Mars was factored into the equations, ensuring the ghost of 3I Atlas would trace the exact same path it had in life. But this cosmic ballet was only the beginning, the simplest part of the equation. The true challenge lay in simulating the star at the center of it all. The sun is not a simple glowing orb. It is a seething cauldron of plasma, a chaotic realm governed by the arcane laws of magnetohydrodynamics. To model it accurately required simulating the behavior of quadrillions of particles, each one a tiny magnet, all caught in an intricate, violent dance. The teams fed the simulations the sun's vital signs from that specific week. They input the precise location, size and magnetic field geometry of every sunspot, every glowing prominence, and most importantly, of that colossal gaping coronal hole turned toward the ecliptic plane, like the barrel of a celestial cannon. This wasn't just a surface-level model. The codes had to delve deep into the sun's convective zone, simulating the roiling currents of superheated gas that generate its magnetic field, the very engine that gives birth to the solar wind. The goal was to create a simulation so robust that the virtual coronal hole would not just look like the real one, but it would behave times like it, breathing a stream of high-speed particles with the same characteristics our Parker Solar Probe had actually measured. Early runs were fraught with digital ghosts and artifacts. Simulations would collapse under their own complexity or produce solar winds that were too fast, too thin, too chaotic. The teams worked relentlessly, tweaking algorithms, refining the physics. It was like tuning a grand cosmic instrument. They adjusted the virtual magnetic field lines, threading them through the corona until they perfectly matched the images from our solar observatories. They calibrated the plasma density, the thermal pressures, the acceleration mechanics, cross-referencing every output with the ground truth data from Parker. It was a painstaking process of digital craftsmanship, a fusion of human intellect and machine power on an unprecedented scale. Slowly, painstakingly, the digital universe began to cohere. The model sun began to breathe. From the dark, open field lines of the virtual coronal hole, a stream of particles began to flow, accelerating outwards into the void. The numbers appearing on the scientists' screens were breathtaking. The simulated wind wasn't just similar to what Parker had detected, it was a perfect match. The velocity profile, the particle density, the temperature gradient, all there. They had done it. They had created a living, breathing star inside a supercomputer. Now for the final terrible act. Into this perfectly calibrated digital stage, they placed the comet, not as a simple point of light, but as a complex physical object. They programmed its known composition, a fragile agglomerate of water ice, frozen carbon dioxide, dust and rock, all held together by the tenuous glue of its own feeble gravity. They gave it a nucleus with the estimated size and rotational period of 3I, Atlas, a delicate tumbling snowball forged in the dawn of the solar system. And then, with the virtual observatories all pointing in the right direction, they pressed run. What followed was a revelation, a chillingly beautiful spectacle of cosmic physics that played out on screen after screen in laboratories around the world. For the first time, we were not just observing the aftermath. We were witnessing the event itself from every conceivable angle. The simulation begins in the eerie quiet of interplanetary space. The digital ghost of 3I, Atlas, glides along its prescribed orbit, a silent pilgrim approaching its closest encounter with our star. Its coma, a fuzzy, glowing shroud of sublimating gas and dust, is already beginning to form a sign of the sun's growing influence. But then, from the left of the screen it comes, not as a flash of light, but as an invisible oncoming wall. The high-speed solar wind stream, born in the heart of the coronal hole, roars through the simulation at over 2 million kilometers per hour. It is a relentless river of protons and electrons, a sandblaster of immense power, and it is aimed directly at the fragile wanderer. The first moment of contact is not explosive but insidious. The simulation shows the outermost tenuous layers of the comet's coma being stripped away, peeled back like layers of an onion by the sheer force of the particle stream. The magnetic field carried by the solar wind, the interplanetary magnetic field, drapes itself over the comet, inducing powerful electrical currents within its ionosphere. This is the unseen initial assault. The beautiful sweeping ion tail, which had pointed directly away from the sun, is violently ripped from the comet's head. The simulation shows it thrashing, contorting, and then completely disconnecting, a phenomenon known as a tail disconnection event, which astronomers had observed but never understood with this level of clarity. The solar wind was literally tearing the comet's atmosphere away from it. But the true devastation was yet to come. The simulation zooms in past the ravaged coma towards the nucleus itself. Here, the full fury of the solar wind is brought to bear. This is not a gentle warming. This is a celestial blowtorch. The bombardment of high-energy particles dramatically increases the rate of sublimation, the process where ice turns directly into gas. The virtual nucleus begins to erupt with violent asymmetric jets of gas and dust, far more powerful than what normal solar heating would produce. These jets act like uncontrolled rocket thrusters on the tiny tumbling nucleus. The comet's rotation, once stable, begins to wobble and spin erratically. The simulation visualizes the immense torque being applied to the fragile body, a gravitational gyroscope being spun out of control. The internal stresses on the loosely packed ball of ice and rock begin to build. On the screen's stress analysis charts turn from cool blue to a critical red. We are watching the comet being shaken apart from the inside out. The particle stream is more than just a force. It is a thermal shock. The surface of the nucleus is superheated by the kinetic energy of the impacts, while its core remains cryogenically frozen. This immense temperature differential creates fractures deep within the comet's heart. The simulation shows these cracks propagating through the virtual ice, spreading like lightning through glass. The icy glue that has held 3I Atlas together for 4.5 billion years is failing. And then, the final catastrophic moment. A particularly violent jet erupts from a newly formed fissure, and the rotational stress exceeds the comet's structural integrity. The nucleus, that primordial messenger from the outer darkness, gives up the ghost. It doesn't explode in a single cinematic fireball. The reality, as shown by the simulation, is both more subtle and more profound. It crumbles. Large fragments break away first, each one becoming its own miniature dying comet, trailing its own shroud of gas and dust. These larger pieces, now with more surface area, exposed to the solar wind, begin to disintegrate even faster, breaking into smaller and smaller pieces. It is a cascade of disintegration, a chain reaction of cosmic dissolution. Within hours, the single bright point of light that was 3I Atlas has become an elongated, indistinct smear of ethereal shrapnel. The comet is no more. It has been scoured into a cloud of its constituent atoms, a ghostly trail of dust and ionized gas that will continue along the same orbit, a funeral procession for a worldlet that once was. The simulation doesn't stop there. The final crucial step is to compare this digital death to the real-world observations. The scientists create a virtual telescope within the simulation, placing it at Earth's position, and ask it to generate a light curve, a graph of the comet's brightness over time. They hold their breath as the two charts are laid over one another. The real one from our observatories and the virtual one from the machine. They are a perfect match. Every subtle flicker, every surge in brightness from an erupting jet, the final tragic dimming into oblivion, it is all there. The simulation didn't just tell a story, it told the time's, true time's story. The mystery was solved, the verdict was in. The coronal hole was not an accomplice, it was the agent of destruction. The solar wind was the weapon, and the impossible alignment was nothing less than a firing solution calculated by the uncaring laws of celestial mechanics. We had witnessed through the lens of our own technology a form of cosmic weather we never knew existed. We saw a star reach out across millions of kilometers of empty space and erase one of its own children from existence. It was a spectacle of profound and terrible beauty, a powerful reminder that the universe is not a tranquil garden, but a dynamic and often violent arena. The death of 3I, Atlas, was no longer a mystery, but a lesson. A lesson that has forced us to look again at the comets in our skies and at the very star that gives us life, with a new sense of understanding and a deep, unsettling awe. For if one coronal hole can do this to one comet, what other secrets, what other powers does our sun hold in its fiery heart? And so the ghost of Comet 3I, Atlas, now haunts the inner solar system. What was once a cohesive body, a frozen jewel journeying for millennia from the abyss, has been rendered into a spectral trail of dust and disenfranchised gas. Its pilgrimage did not end in a blaze of glory against the sun's fiery surface, nor did it round our star to begin a triumphant voyage back to the cold darkness. Instead, it met its end in a far more subtle and in many ways more terrifying manner, becoming not the spectacle we had hoped for, but the lesson we so desperately needed. This was not merely the death of a comet. It was a celestial autopsy performed live on a cosmic scale, compelling us to rewrite our understanding of the very space that separates the worlds of our solar system. We watched expecting the simple physics of heat and gravity to govern its fate. We anticipated a gradual sublimation, the sun's warmth gently peeling away its icy layers, a predictable and well-documented process seen in countless comets before it. But Atlas did not follow the script. It encountered something else, a force we knew existed but had never witnessed in such a devastatingly clear and consequential alignment. It flew into the path of an invisible storm, a directed torrent of energy erupting not from a sunspot's violent flare, but from a dark, gaping wound in the sun's own atmosphere, a coronal hole. This was not a bomb. It was a celestial blowtorch, a focused jet of solar wind, a million-mile-per-hour gale of charged particles that scoured the comet's soul. The high-speed stream was an unrelenting, abrasive force, stripping away not just the comet's gaseous coma, but its very structural integrity. Imagine a ship of ice sailing into a river of acid. At first, the damage is imperceptible, a slight etching on the surface. But the current is relentless, the corrosive agent all-encompassing. The ship's defenses, its magnetic field, its outgassing shield begin to buckle and fail. The acid doesn't just melt the ice. It finds every microscopic fracture, every point of weakness within its structure, and pries it open with relentless pressure. This is what happened to 3I Atlas. The fast solar wind didn't just push against it, it infiltrated it. The stream's turbulent magnetic fields churned and twisted the comet's own delicate magnetosphere, inducing electrical currents deep within its nucleus that violently heated the interior. Frozen gases trapped for eons likely erupted from within, shattering the comet from the inside out in a cascade of fragmentation. We saw the nucleus, once a singular point of light, begin to fracture into a family of ghosts, each a smaller, dying ember of the original whole, before they too dissolved into nothing. The spectacle we witnessed was the death rattle of an ancient traveler, dismembered not by a singular cataclysm, but by a persistent, invisible torment. It was a profound and sobering revelation, forcing us to abandon our simpler models and confront a far more complex and hazardous reality. For decades, our perception of the space between planets was that of a near vacuum, a mostly benign emptiness punctuated by the occasional solar storm. We saw the sun's influence primarily through light and heat, and the more dramatic outbursts of coronal mass ejections. The general ever-present solar wind was seen as a kind of cosmic weather, a steady breeze that shaped the tails of comets and buffeted planetary magnetospheres. The demise of Comet Atlas has irrevocably shattered that perception. It has proven that this weather can become a weapon of immense destructive power, and that its most potent forms are not always the most visually spectacular. A coronal hole appears as a dark, quiet patch on the sun, an area of seeming tranquility. Yet we have now seen that these regions of open magnetic field lines are the nozzles for the sun's most focused and sustained energetic fury. This changes everything. It forces us to re-evaluate the life cycles of comets, especially the so-called sun grazers. How many of these celestial visitors, which we assumed simply vaporized from raw heat, were actually torn apart by these solar wind streams long before they reached their closest approach? How many cometary families, those clusters of fragments moving in similar orbits, were not born from gravitational stresses near a giant planet, but were instead the shattered remains of a parent body that suffered the same fate as Atlas? The comet's sacrifice provides a new lens through which to view cosmic history, a new potential culprit in the grand celestial detective story. We are now compelled to look back through our archives to re-examine the unexpected fading or fragmentation of past comets, searching for the telltale signature of a coronal hole alignment. What we once dismissed as an inherent structural weakness within a comet might have been the result of an assault by an unseen external force. The solar system, it turns out, is not an empty stage where objects simply follow the laws of gravity. It is an active environment, an ecosystem of energy and magnetism, and the sun is its undisputed and often ruthless architect. This newfound knowledge extends far beyond the realm of academic curiosity, reaching directly into the heart of our technologically dependent civilization. The very same streams of high-energy particles that disintegrated a comet pose a clear and present danger to the fragile infrastructure we have placed in orbit, and even to our power grids on the surface of the Earth. Space weather prediction has until now largely focused on the big explosive events, the solar flares and coronal mass ejections that send billions of tons of plasma hurtling our way. These are the hurricanes of the solar system, and we have become adept at spotting them as they form, giving us precious hours or even days of warning. But the high-speed streams from coronal holes are different. They are more like cosmic jet streams, persistent and long-lasting, that can buffet Earth's magnetic field for days or weeks at a time. As the sun rotates, these holes can spray the solar system like a garden sprinkler, and if Earth passes through one of these streams, the consequences can be severe. These streams can induce geomagnetic storms that overload power transformers, disrupt high-frequency radio communications, and create navigational errors in GPS systems. They fill the radiation belts around our planet with killer electrons, threatening the delicate circuitry of the thousands of satellites we rely on for everything from financial transactions to weather forecasting and global communication. Astronauts on the International Space Station and those who will one day journey to the Moon and Mars are exposed to higher doses of radiation, increasing their long-term health risks. The death of Comet Atlas serves as a stark and visceral demonstration of the sheer power contained within these streams. It is a cosmic canary in the coal mine, warning us that we have been underestimating one of the most persistent threats our star produces. Our models must now evolve. It is no longer enough to simply watch for explosions. We must meticulously map these dark, open wounds on the sun's face. We need to model the trajectory of their particle streams with far greater precision, predicting not just when they will arrive, but their density, velocity, and magnetic orientation. The fate of a small, insignificant comet has handed us a vital piece of the puzzle for protecting our entire global infrastructure. In its silent, graceful dissolution, Atlas screamed a warning we can no longer afford to ignore. We must learn to forecast the invisible rivers of space, because we, like the comets, are sailing directly through them. And this leads us to a darker, more unsettling question. If a coronal hole stream can dismantle a comet made of ice and rock, what might one do to an object on a direct collision course with Earth? The threat of a killer comet or asteroid has long been a spectre haunting our collective imagination, a terrifyingly random act of cosmic violence. Our entire planetary defense strategy is built on a simple premise: find the threat early, calculate its trajectory with precision, and devise a way to nudge it off course years or even decades before impact. This strategy relies on the assumption that the object is a single, solid, predictable body. The lesson of 3I, Atlas, introduces a terrifying new variable into that equation. Imagine we detect a large comet years out on an impact trajectory. Our telescopes track it, our computers model its path, and we prepare a mission to intercept it. But then, on its journey toward us, it passes through a powerful, sustained solar wind stream, just as Atlas did. The stream begins to fracture the nucleus. Instead of one solid object to deflect, we are suddenly faced with a dozen or 100 smaller, unpredictable pieces. The single bullet has become a shotgun blast. Some fragments might be pushed onto trajectories that miss Earth entirely, but others could be shifted to strike different locations at different times. The cohesive, predictable threat dissolves into a chaotic cloud of impactors, overwhelming any defense system we could possibly mount. Furthermore, the outgassing caused by the stream's bombardment could act as a natural, unpredictable thruster, subtly altering the comet's course in ways our gravity-based models would fail to anticipate. A small, non-threatening comet could be nudged onto a collision course. A predictable impactor could have its arrival time and location scrambled. The Sun, our life-giving star, could inadvertently become an accomplice, pre-processing an incoming threat in a way that makes it infinitely more dangerous and complex. The study of coronal holes and their interaction with small bodies is no longer just an astronomical subdiscipline. It is now a critical, non-negotiable component of planetary defense. We must understand this process not just to protect our satellites, but to ensure we are not blindsided by a cosmic threat that has been transformed and multiplied by the Sun's invisible arsenal. In the end, the story of Comet 3I, Atlas, is a profound parable about our place in the universe. We look out into the cosmos filled with a desire to understand, to predict, to control. We build ever more powerful observatories, launch ever more sophisticated probes, and construct elegant models that seek to tame the chaos of the heavens with mathematics. And just when we believe we have a firm grasp on the rules of the game, the universe reveals a new layer of complexity, a new force, a new interaction that humbles us and reminds us how much we still have to learn. The comet's journey from the frigid outer darkness into the heart of the solar system mirrors our own journey of discovery. We venture forth from our own small protected world into the vast unknown environment of space, and with every step we encounter unforeseen challenges and beautiful, terrible new truths. The sun, the anchor of our existence, is not a simple, steady furnace. It is a living, breathing entity of unimaginable complexity, a seething ball of plasma governed by magnetic fields so intricate they make the most complex weather systems on Earth look trivial. Its influence extends far beyond the light that warms our skin. It is a dynamic presence that actively shapes and scours every corner of its domain, and its moods can mean the difference between life and death for a wandering comet or between a functioning society and a global blackout here on Earth. The death of Comet Atlas was not a failure of observation, but a triumph of it. It was a moment when nature pulled back the curtain, however briefly, and showed us a mechanism we had never seen in action before. It was a gift of knowledge purchased at the cost of a celestial wanderer, and now its legacy is all around us. The very particles that once made up its nucleus, now ionized and captured by the solar wind, are streaming outwards through the solar system. Some of that dust, that final ethereal remnant of 3I, Atlas, will one day rain down through our own atmosphere, settling invisibly on the surface of our world. A final silent message from the void reminding us that we are inextricably linked to the grand, violent, and magnificent symphony of the cosmos. A reminder that there are still great mysteries to be solved, not just in the distant galaxies, but right here in our own stellar backyard, in the enigmatic heart of our very own Sunday. Our quest for understanding continues, invigorated and redefined by the ghost of a comet that came to us not as a spectacle, but as a teacher,